I want to do one more, at least one more Hamiltonian problem. Hamiltonian mechanics. And I've seen this problem more than once, so I thought it'd be a good example. Here's the problem. There is a cone, with a mass constrained to the surface of the cone, and there is a gravitational force. So this is up. There's a gravitational force pulling down. So let's just model the motion of that. I like this problem because it's 2 degrees of freedom, which we don't always do with Hamiltonian mechanics. So a quick review of Hamiltonian mechanics. So the first is we have this Lagrangian, which is the kinetic energy minus the potential. You actually need to find that to do the Hamiltonian mechanics. With that, we can define coordinates of momentum. So this is pi. We can have more than one momentum, and we're going to have 2 degrees of freedom here. We're going to have the z coordinate, and then we will have the theta coordinate. So theta is the angle in the xy plane. So I can define momentums from the Lagrangian, the partial of the Lagrangian with respect to each coordinate. So the partial of L with respect to 0, z will be pz. The partial of L with respect to theta will be p theta. From that, I can write down the Hamiltonian, the sum of the p's and q dots, and remember q dot means derivative with respect to time, minus the Lagrangian. And so there will be 2 terms there. I'll have a p theta, theta dot, a pz, z dot term. And then I can get first order differential equations of the q's and p's. The partial of h with respect to p is q dot, and then negative the partial of h with respect to q is p dot. So I'll actually get 4 differential equations, right? I'll get 2 for theta and 2 for z. Okay, let's get going. We got some work to do. And yes, I'm going to model this in Python because it will be fun. And I'll probably make a phase space diagram, but we'll see. The number one thing is this equation for the cone, right? If I want to find the position from the z-axis, it's just a times z, so that defines the surface of the cone. So I can't have any r value. It has to depend on z. Of course, we're going to use cylindrical coordinates here. So I have x is r cosine theta, y is r sine theta. So it looks like 4 coordinates here, but we really only have 2, right? Because the only 2 that can change are z and theta. R depends on z, and x and y depend on r and theta. So z and theta. Let's go ahead and write down the Lagrangian. The first thing we need to do is to get the kinetic energy. And so it's not completely obvious what the kinetic energy is. We always want to write the kinetic energy in terms of Cartesian coordinates, in which case it is easy. And that's going to be equal to 1/2 the mass times x dot squared plus y dot squared plus z dot squared. Now I can get x dot y dots from these equations up here. So let's do that. I'm actually going to need r dot too. So let's go ahead and take all these derivatives. R dot is going to be a z dot. That one's pretty easy. X dot is going to be equal to r dot cosine theta, right? I have the product rule, so I have to take the derivative of r times cosine theta plus r times the derivative of cosine theta, and the derivative of cosine theta is negative sine theta theta dot, because I have to take the derivative inside. So I can get minus r theta dot sine theta. And then y dot is going to be equal to r dot sine theta plus r theta dot cosine theta, because the derivative of sine theta is that. Okay, so now what I want to do is to at least deal with z dot squared is easy. Let's get the sum of these two. So let's take x dot squared plus y dot squared. I'm going to write this out the full way. So if I'm going to run out of room because it gets a little bit messy, not too bad. So let's just write this as x dot squared is going to be equal to, let me scooch this up. Scooch is a correct word there, scooch. X dot squared is going to be equal to r dot squared cosine squared theta. I'm going to get that term. I'm going to get the 2 of the cross terms. So minus r dot theta dot cosine theta sine theta, and then that term plus r squared theta dot squared sine squared theta. Now let's put the y dot squared below it. Y dot squared is going to be equal to this squared, r dot squared cosine squared theta. And then I'm going to get the cross term, which is going to be plus r dot theta dot cosine theta sine theta, and then I'm going to get that squared plus r squared theta dot squared cosine squared theta. So maybe you can see what's really nice here, because x dot squared plus y dot squared is going to be equal to, let's break this up right here, these two terms cancel. Yay. Oh, there's a 2. Isn't there a 2? It doesn't really matter. I get this times that. Yeah, there's 2. It doesn't matter. These two terms I can sine. That was 2 mistakes there. Sine squared theta. Okay, I got it right up here. Here I can factor out an r dot squared, and then I get cosine squared plus sine squared, which is 1. And then over here I can factor out a r squared theta dot squared, and then I get sine squared plus cosine squared, which is 1. So that's it. So now I can write my kinetic energy term. T is 1/2 m r dot squared plus r squared theta dot squared plus z dot squared. Now I can get rid of the r and the z too, or r and the r dot. Remember, r is a z, r dot is a z dot. So if I do that, let's go ahead and write down the whole Lagrangian. Why not, right? Why not? L is t minus u. U is just mgz. So I get 1/2 m. R dot squared is going to be equal to a squared z squared. R squared is going to be dot a squared z squared theta dot squared plus z dot squared minus mgz. And then so we can combine these two z dot terms. So I get 1/2. I don't know why I just brought the m a squared plus 1, no, plus m z dot squared plus 1/2 m a squared z squared theta dot squared minus mgz. Is that right? I think that's right. Yeah. I could pull that m out, but I don't need to. Now I can use the Lagrangian to find my two momentums. So pz is going to be the partial of L with respect to z dot. So if I do that right here, I have one z dot term. Isn't that right? Yep. So I bring the 2 down and I get m a squared plus m z dot. And I can do the same thing. P theta is the partial of L with respect to theta dot. And there's only one theta dot term right here. So I bring down the 2. I get m a squared z squared theta dot. Now we can go ahead and write the Hamiltonian. H is going to be pz times z dot plus p theta times theta dot minus L, which is going to be minus 1/2 m a squared plus 1 z dot squared minus 1/2 m a squared z squared theta dot squared plus mgz. Now, you may be tempted to say, oh, the Hamiltonian's the energy. I'm going to write down the kinetic plus potential. But there are some cases where that's not true, so I recommend doing it this way. Now, the problem is that we have z dots and theta dots. We want to have this Hamiltonian in terms of pz, theta, and z. No dots. Okay. So that means I have to get rid of theta dot, I have to get rid of z dot. So up here, I can solve for z dot in terms of pz. So this says that z dot is equal to pz over m a squared plus 1. And this says theta dot is equal to p theta over m a squared z squared. So I can substitute that in right there, right? I can make a substitution. Instead of z dot, I put this. So this gets a little bit messy, but we'll see what's going to happen in just a second. So let's write it out. H is pz times this, which is pz squared, over m, parentheses, a squared plus 1. And then this term is going to be plus p theta times this, which is p theta squared, over m a squared z squared. And then I'm going to get minus 1/2 m a squared plus 1. What's that term? Z dot squared is going to be equal to this squared. So I actually get pz squared over m squared a squared plus 1 quantity squared. And then over here, I get minus 1/2 m a squared z squared theta dot squared. But theta dot is this, so it's going to be p theta squared over m squared a to the 4th z to the 4th. And then I have plus mgz. Now, right here, this term is the same as this term, right? Because that cancels. This cancels with one of those. That comes with that. But I have a negative 1/2. So if I add those two together, I just get the half of this. So I have h is pz squared over 2m a squared plus 1. And the same thing's true here. This term is twice of that term because of the cancellation. So I get plus p theta squared over 2m a squared z squared. And then I have that term right there plus mgz. So now we have our Hamiltonian. We are rocking and rolling. That's a thing. It happens. Okay, but you have to have your paper straight. I don't know why. I'm not like really a neat freak person, you know. I don't really have, but when it comes to paper, I like to look at it on the screen and see that it's all lined up. It's just my one little thing. It's kind of weird. Okay, so we can go ahead and do Hamiltonian to get 4 equations. So let's do this. I kind of forget which one has the negative. I already put it up here. The partial of p, the partial of h with respect to p. So the partial of h with respect to pz is going to be equal to z dot. So if I do that, z dot is going to be equal to the partial of h with respect to pz. So here's my pz. I bring the 2 down, and I get pz over m a squared plus 1. And there's no other pz's, which is not surprising because that's what we had before, right? That's how we define pz. So we should still do it. Now let's go ahead and find pz dot. Pz dot is negative the partial of h with respect to z. So if I go down here, I'm looking for the z's. There's no z in this term. Here is a z. So here I have a z to the negative 2. So if I bring that down, then that cancels with that, and I get p theta negative. I get negative and negative, so I get p theta squared over m a squared z cubed. And then I have that term too, but there's a negative, so I get negative mg. And this, if you just want a little insight, this is the change in momentum in the z direction. This is the gravitational force, and this is I think this would be component of the gravitational force and the z and the normal force, the centrifugal force really in the z direction. I'm not 100% sure, but that's what that is. Okay, so that's good. Now let's do theta. So the partial of h with respect to p theta is going to be equal to theta dot. So I'm up here. Theta, the partial with respect to p theta, that's a theta. Here's my only p theta, so I get p theta over 2m, no, I don't get the 2. P theta over m a squared z squared, which is again my definition of theta dot, so that's not surprising. And then p theta dot is going to be equal to negative partial of h with respect to theta, which is 0. There's no thetas in there. So that says, that's important. That says p theta does not change. I feel like I need a new marker. My marker's getting a little weak, but that's fine. So now I have 4 first order differential equations, and I can use that to solve the whole problem, which I'm going to do numerically. So here's how this is going to work. I'm going to break it into small time steps. And the first thing I'm going to do is to calculate pz dot, right, based on this. And p theta dot, which doesn't change, but I can calculate, it's 0. Okay, so I'm going to calculate pz dot. I'm just going to put what it is. And then I'm going to set that equal to delta pz over delta t, which is going to be pz2 minus pz1 over delta t. So this is a short time interval. I'm assuming pz dot is constant. So I can get from this pz2 equals pz1 plus pz dot delta t. So I can update pz. I could do the same thing with p theta, but it's constant, so it doesn't really matter. So I just have p theta equals p theta 1. Let's say that. Which is and so this is the initial, I need the initial pz, I need the initial p theta. And now I can go over here to, once I do that, I can calculate z dot equals this. So I'm going to calculate that. And then set that equal to delta z over delta t, or z2 minus z1 over delta t. So I get z2 equals z1 plus z dot delta t. So I can update z. And then I can do the same thing with theta dot. And then once I know theta dot, I can say that's delta theta over delta t. And that is going to be equal to, so then I get theta 2 equals theta 1 plus theta dot delta t. And so I calculate theta dot with this. And you notice that even this p dot's 0, but p theta is not 0, and z is not 0. So that does change. And then I do the whole thing over again. Okay, let's do this in Python. So in Python, I am going to need some numbers. So let's say a equals 1/2. That's my coneness. Let's say m equals 0.05. I'm just picking stuff here. And then I'm going to need to get an initial z. So z equals 0.2. Z dot is going to be equal to 0.1. I'm just picking stuff here. Theta equals, it doesn't really matter, 0. Theta dot initial is going to be, let's say, 6. I think I have everything. And then g. Okay, so let's use that. So going over to Python. The first thing I want to do is, and I already put 2 things in here. Surprise. I got a little jump start. The first thing I'm going to do is to make a cone. Okay. Now I'm going to have z as the direction of the vertical, which I would normally do y. So, but that's fine. I've tried to change it before, and it just messes up my mind, and I make a mistake. So I'm not going to do that. So let's make my cone. Let's call it it's not a cone because cone's the object. Let's call it a horn. It's not a horn either. The horn is a type of an object called cone. Now, in Python, the cone is actually backwards. You define the top part as the position, the big part, and then the vector from the top to the end is your axis. So I'm going to put this at, let's say, s equals 0.4. So if that's the case, I want my top I want the pointy part at the origin. So I'm going to say position is equal to vector 0, 0, s. And now my axis is going to be a vector from there down to the origin. So axis is going to be equal to vector 0, 0, negative s. Now my radius, if I put in, it should be just s times a, right? A times s. Because that will be my r value at the top. And let's just run it. Okay, so there's my cone in the z direction, which comes out of the page. Okay, so x is, I get that backwards. Well, y is that way. And there's my cone. It looks nice. Okay, let's do one real quick thing. Opacity equals 0.3. So now we can see through it. Okay, that's nice. Nice cone. The next thing I want to do is to make my mass. So m equals, what did I say it was? 0.05, 0.05. And we need to make an object for that mass. So I'm going to call it a ball. But to do that, I'm actually going to say, where do I want to start it? Let's give it z equals 0.2, so halfway up the cone. And then theta equals 0. Let's just start, because it doesn't really matter. So now I can say r equals a times z. And now I can say x equals r times cosine theta. Y equals r times sine theta. I need to go back to Cartesian coordinates to draw my objects because Web VPython uses Cartesian coordinates. Now I can say ball is a sphere. Gotta spell it right though. Is this big enough? Hey, that's bigger. Position is going to be equal to the vector x, y, z. Isn't that nice? Radius is going to be equal to, let's say, s over 40. Color equals color.yellow, so it shows up nice. Make trail equals true. Let's run it and see what that looks like. Okay, so there's my mass. Okay, that looks nice. Good size. Everything's good. Okay. Now I need a couple more things. I already said my initial I have z, I have theta. I need z dot theta dot pz dot p theta dot. So I said z dot is equal to 0.1. Maybe that's too high. That's fine. Theta dot is 6. And I always have trouble estimating initial angular velocity, but that's fine. Now I need to calculate, I don't want to do z dot and theta dot. I just want to do this in terms of momentums, right? So looking back at my equation, I have pz is ma squared plus mz dot. So let's say pz dot is equal to m times a squared plus 1 times z dot. And I'm only doing that because I'm thinking in terms of z's. I have trouble thinking in terms of momentum. P theta dot is equal to, I'm looking at the equation for p theta. It's going to be m times a squared times z squared times theta dot. Tough. Okay, cool. Now I have my initial conditions. Those are my initial conditions. T equals 0, dt equals 0.001. Now we're going to make a loop. Let's run it for 5 seconds. So while t less than 5, rate 1,000. So that means don't do it more than 1,000 calculations per second. So it'll run in 5 seconds. And now I'm going back over here. The first thing I want to do is to calculate pz dot. I'm going to calculate pz dot. So pz dot, oh wait, no, that's pz. That's pz. Yeah, this is pz and pz dot, and theta, and p theta, not dots. P theta. And that is the right equation though. So pz dot is going to be equal to the equation that I calculated, which is p theta dot squared, p theta squared, divided by m times a squared times z cubed minus m times g. Now I'm going to calculate p theta dot, which is 0. So I'm going to do it anyway. Now I'm going to use those two to update the p's. So I'm going to say pz equals pz plus pz dot times dt. P theta equals p theta plus p theta dot times dt. And yes, p theta doesn't change, but that's fine. Now I'm going to use those values and calculate z dot and theta dot. So, oops, that's weird. Z dot equals, again, looking over at my equation, z dot is going to be pz divided by m times a squared plus 1. And then I'm going to say theta dot is equal to, looking at my equation, p theta divided by m times a squared times z squared. Now I can update z. Z equals z plus z dot times dt. Theta equals theta plus theta dot times dt. And that's it. Except I need to update time. T equals t plus dt. And I need to move my ball, right? So if I want to move my ball, I have to recalculate x, y, and z. I already have z, but I need to get x and y. So I'm going to say r equals a times z. And then x equals r times cosine theta. Y equals r times sine theta. And then I'm going to move the ball. Ball.pos equals vector x, y, z. Will it run? Will it run? You just never know. You really don't ever, never know. Okay. That's strange. Is it moving? Maybe my theta dot's not high enough. Let's put that at something larger. Let's say 12. It's just moving up and down. I'm not changing my theta. Theta dot. Oh. It's your job to catch these mistakes. And so let's go back down to the 6. I knew something was wrong, because if you have no theta dot, initial theta dot, it's going to go down towards the cone, and then it doesn't know what to do, because it's like, I don't know how to do that. It doesn't handle at the origin very well. So theta dot is where? Right there. Let's put this back at 6. I think 6 will work. Okay, I'm pretty happy. That looks good. So the thing I like about this is you'll notice that you can't get down to, it's a little jaggedy. I might need a smaller time step, but I'm pretty happy with that. That's actually just artistic right there. You can't get down to the cone, right? Because if angular momentum is conserved as you go down to the origin, to the r equals 0, it's going to speed up, and so it's never going to be able to get down to that cone if it starts with an angular velocity. Let's make it go a little bit faster. Let's just try making a slightly smaller time step too, because I want it to be a little bit smoother, but I'm not really sure. Okay, I'm pretty happy with that. That's pretty cool. Okay, so, ooh, look at that. Let's go ahead and make 2 phase space plots, just to see what happens, just for fun. Because when we do Hamiltonian, we like to do phase space. So G1 equals, let's call it GZ is a graph. I'm just going to put the X title equals Z. Y title equals Z dot PZ. And then width equals 250 by 250. And I think if I do this, a line equals left. I can put them side by side, I think. And then we'll call this FZ is G curve. Color equals color dot blue dot equals true. And then let's do the same thing for theta. Copy all that. And let's call this GT. And this will be theta, P theta. And then align equals right. And I think this align thing I need to check. If it doesn't work, I'm just going to get rid of that. And then we'll call this FT, and we'll make that one red. So I want to plot momentum versus coordinate. So down here, I'm going to add those two things. So I'm going to say FZ.plot Z PZ. And then FT.plot theta P theta. Let's see what that looks like. Oh, yeah, it did it. Okay. Yeah, that's pretty good. You'll notice that the phase space plot for theta is weird in two ways. Weird way number one is that it doesn't change. Well, in the p theta. But remember, p theta dot was 0, so it's not going to move up and down. Number two, since it's a theta coordinate, theta just keeps increasing even though it spins around in a circle. We could fix that by saying if theta is greater than pi over 2, theta is equal to 0. And I think that would work. But that's fine. I don't really care. So there's the z one, the pz is more fun. And that shows basically how it's moving up and down. And I'm pretty happy that I've got these side-by-side graphs. That actually made me a little bit happy. Okay, that's it at the end. That's this code. I'll give you a link to this code and Hamiltonian mechanics.